All right, today we're talking about Chapter 3, Section 2. And so, Chapter 3, Section 2, if you did not like having to um, uh, figure out the critical points and if it's a relative minimum or relative maximum, doing the whole, looking at this interval, plugging in a point, test point, da da da, then I got good news for you because there's a faster and better way to do it, and that is using the second derivative. All right, obviously we have to take the second derivative, but I mean I would much rather take the second derivative of a function than than do the whole critical points and then test points for those critical points. Something that's also going to be a little rough today is since somebody's in here working on a microwave, um, my cat, he also happens to be in here because he's scared out there. So and he's very lovey. So if anything just happens to just shoot off the screen, it's because he's rubbing his face on it and he won't stop. All right, so lots of snipping here on. I'm just going to try and get these all out of the way before I begin the process of explaining what we're talking about. Jeez. Okay. So I guess we'll put this on that page, and then we'll put example one, and then I'll maybe begin the lecture. Can we? That should work. All right. So how many pages did we snip there? Here we go. So concavity. What is concavity? Well, concavity. Where are we at? Let's just start here. So for the graph of f, the slopes of the tangent lines are increasing. That is, f prime is increasing over an interval. This can be determined by noting that f double prime, the second derivative of f of x, is positive, since the relationship between f prime and f double prime, the first and second derivative, is like the relationship between f and f prime. So for graph G, the slopes are for the graph of G, the slopes are decreasing. This can be determined by noting that, same thing, well, opposite rather. Okay, so when we talk about concavity, it is what you think it is. No, we can see here this particular graph is concave up, and we can see here this particular graph is concave down. Right, so these are the ideas and I guess the definitions of concavity. Now, how do we test for concavity? How do we know if we're concave up or concave down? All right, and real quickly, before we dive too deep into this, I want to point out, all right, there's a reason why we're figuring out all this stuff, and that's so we can graph equations. All right, so being able to graph functions, I guess. So we need to be able to graph functions, and being able to determine the behavior of functions is how we do it. Some of you, well, many of you, hopefully all of you, I don't know, went through pre-calculus algebra, at least went through college algebra, and hopefully you remember that in those courses we also learned how to um, come up with a graph using multiplicity and in behavior and things like that. And those can only tell you so much. Whereas now what we're trying to do is we are going to figure out, we're going to pin down exactly how to graph an equation, and we're using derivatives as opposed to just the whole, solving for zero and then looking at in behavior and such. So that's the whole point of being able to learn how to do this. So anyways, so a test for concavity, it's super duper easy. However, I do suggest that you obviously, write this down, put a star beside it. So if the second derivative of our function is greater than zero, um, see, should be, Well, yeah, I guess I mean that is technically true. If the second derivative of x for all x on an open interval of I, um, but what we're going to do is we're going to be testing our critical points, and that those are pretty much the numbers that we're going to be looking at. If the second derivative of our function is greater than 0, then we're going to be looking at a concave up. And if the second derivative of our function is less than 0 at some point, we're going to be testing the critical point mainly, then we are concave down. So makes sense, right? If we're greater than 0, we're concave up. If we're less than 0, we're concave down. So yeah, I don't have to read all that, but they are in the notes. All right, so here's some examples of what concave down looks like. Right? I mean, it could be so minute that it doesn't really register. But I mean, it's a concave down. There's also concave down, and these are just ideas of concave up as well. And of course, you'll get a better idea of this once we get into actually doing the work. I don't think we need that. Well, I mean, we need it, but it's in the notes. I try to word things a little differently to at least pretend like I'm doing my job. So we have another theorem here, and this one is also one of these that you need to put a star beside. So suppose that some function is differentiable for every x on the open interval. So basically that first sentence is just to let you know, it's just to be an airtight theorem to say, look, you can only do this on differentiable functions. And that are differentiable functions on some interval. And that there's a critical value c in AB for which the first derivative of c is equal to 0. And again, we talked about, c is between a and b. I know it doesn't seem right, but you just kind of get used to it because the intervals a to b are used quite often. But anyway, so if the function at c, it's going to be a relative minimum if the second derivative there is greater than 0. Okay, so instead of doing the test points like we did before and figuring out the test points and then see if they're greater than or less than 0, we get to save about, I don't know, 2 minutes, maybe one. I don't know, depends how quick you are. 1 or 2 minutes of computation time by just figuring out the second derivative and plugging in our critical point. And depending on if you're greater than 0 or less than 0, you can figure out if you're a relative minimum or relative maximum, respectively. Let's not. Again, I'll just keep that on the notes. And instead, we'll just jump straight here to the first example. So the first example reads, find any relative extrema and graph the function f given by f of x is equal to x cubed plus 3x squared minus 9x minus 13. Alrighty, so the first thing we're going to do is we're going to find the first derivative, and lucky for us, this is going to be a pretty easy first derivative, right? So I don't really like my toolbar being this high. There we go. Okay, so f prime of x, sorry, f prime of x is equal to, all right, so x cubed, that's going to be 3x squared plus 6x minus 9. Okay, that's the first derivative. And let's go ahead and I'm gonna take a hair off my screen, and then let's go ahead and take the second derivative just while we're in the mood to take derivatives. So the derivative of this of f prime of x is going to be 6x plus 6. Okay, so we figured out the first and second derivative. And so now we have to figure out, the example wants us to find any relative extrema and then graph the function. Okay, so in order to figure out the relative extrema, what we're going to have to do is we're going to take the first derivative. Okay, remember we have to get critical points, so let's just go ahead and do that. So step 1, we're going to find critical points, C, P. Okay, so in order to do that, we have to take the first derivative and we're going to equate it to 0. Okay, so we're going to do 3x squared plus 6x minus 9 is equal to 0. Again, this is the exact same thing we did in the previous section, so it shouldn't be anything new. And so if we factor this, we end up with x plus 3x minus 1. Did we do this last time? Is equal to 0. And so that means that we have a critical point. We have critical points at x is equal to a -3, and x is equal to a positive 1. Okay, so these are our critical points. And what we're going to do is we're going to take these critical points and we're going to put them into our second derivative. Okay, our second derivative here. So step 2, I don't know, how should I word this? Just, I don't know, put into second derivative. Put into pi, we'll put pi f double prime of x. All right. So put in the second derivative. So if we do the first one, we're going to plug in -3 into the second derivative. So we're going to end up with, well, let's just do this. Let's write this very thoroughly here. So we're going to do f prime of -3, and that is equal to, well, that was equal to what? 6 times -3 plus 6. Well, 6 times -3 is a -18, plus 6 is a -12. Okay, and then we're just going to leave that there just for a moment. And then f double prime of 1, and yes, I love to do my multiplications by 1. So it's 6 times 1 plus 6, which is equal to positive 12. Alrighty, so what does this tell me? Well, looking at my by plugging in my critical points into my second derivative. All right, let's go back to the previous page real quick. All right, this reads, if we plug in my my critical point and we're greater than 0, all right, we had one that was greater than 0, and that was the positive 12. I'm trying to hit next, it's not working. Uh-oh. Oh no, did my screen freeze? Alright, that is unfortunate. I have not had that happen yet. I can't even undo it. Uh-oh. There we go. Okay, so I don't know what happened, but whew. Oh, that's just going to stay. I don't care about it. Oh yeah, so anyways, so back to what I was saying. We had the critical point be the when I plug it into my second derivative, it's greater than 0. So this tells me that, oh no, is it to mess up again? Is it this page? We're not going to flip back and forth. We're just going to assume what I say is true here. So since this is a -12, all right, this tells me that since it's less than 0, it's going to be a relative maximum. So let's go ahead and put what in the world is going on? This is going to be a maximum. And since this is greater than 12, it is going to be a minimum. Okay. So we found some relative extrema. We know that at -3 we are a maximum, and at positive 1 we're going to be a minimum. So now we need to graph the equation, because it says graph the equation. So let's, okay, I think that's just going to stay. Super duper unfortunate. So I'm gonna actually try to give this a good old college try to kind of drive the point home, and then I'm gonna just let the textbook draw cleaner graphs. But anyways, so we have critical points at a what was a positive 1 and a -3, right? So we have critical points at x is equal to -3 and x is equal to a positive 1. Okay. So what I need to do is I need to figure out, okay, so I need to figure out the y coordinate here, right? So the y coordinate, I'm scared to go back a page, of this function. So figuring out the y coordinate, what we're going to do is we're going to have to plug in those values into our original equation. So let me get my calculator out here. So I'm going to plug my critical points into my original equation, right? My critical points are x values, and I need y values. So I'm going to behind the scenes here on my calculator, I'm going to do f of -3, plug in -3 in all these, and figure out my y coordinate. And then I'm going to plug in f of 1 and put it in here and figure out my y coordinate. Actually, I can do 1 in my head, but and again, these critical points are gathered from the first derivative. Okay, so real quickly, let's go ahead and do this. So 14. Okay, so I got 14 for -3, and for +1, 1 keeps 1, 1, 9, 13, and -18. So I'm going to have points -3 and 14. So one of these points is going to be -3, 14, and the other point's going to be a 1 and, shoot, is it -18, I think? Okay. So, that's unfortunate. I'm going to have to go really far out. All right, so oh man, this sucks. So each one of these is going to be 2. Each one of these tick marks I'm making me 2. Hopefully it works out. Okay. So again, each one of these tick marks are going to be 2. So if I were to, I'm going to have to go this way too. Shoot, I have to go right in the middle. And whatever. Okay. So let's go ahead and point these. So -3, 14. If I go over here, again, this is -2. So I'm going to go in between, and then to +14. Sorry, +14. So we go 2, 4, 6, 8, 10, 12, 14. 2, 4, 6, 8, 10, 12, 14. So about right here. And then at +1 and -18. So that's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18. About right here. Hopefully. All right. All right. So these are our critical points, and we figured out that -3, 14 was a relative maximum because if we go back, when I plugged in -3 into the second derivative, it was a negative number, which told me it was a maximum. And we know that 1 is a minimum because when we plugged it into the second derivative, we got a positive number, which means that it is a relative minimum. And of course, you can kind of see that because I mean, it's down here and this is up here. And from there, we can, pretty much figure out, well, this graph, obviously doesn't have any holes in or anything. It kind of goes something like, I don't think the book's graph looks anything like this, but it kind of looks like this. All right. I know the textbooks doesn't look like that. How in the world did they do it? Oh, their x coordinates are a lot wider. Okay. Well, anyways, let's go ahead and snip this and give you a nice, clean looking graph. Right there. Yeah, so I made my tick marks all even around. This one, the textbook made the x-axis a lot wider. That's fine, nothing wrong with that. But that's how we graphed it, right? So we got the first derivative, got our critical points, and then got our second derivative, plugged the critical points into the second derivative, and if we were positive, we knew that we were concave up. If we were negative, we were concave down. And all right, so now we get to jump into example 2. Man, this is not good. I've got two toolbars over here. Alrighty. So example 2, find any relative extrema and graph the function k given by our function k of x equal to e to the 2x minus e to the x. And like I've said before, we whenever I see e's, I'm always like, oh, geez, e's. But then I remember, the derivatives aren't that hard, right? So let's go ahead and work on that. So let's put that in, this is in yellow actually. F prime of x is equal to, well, the first derivative is pretty easy, right? It looks like it's just e to the 2x and then the derivative of 2x, which is 2. So it's going to be 2 e to the 2x. And then the derivative of e to the x is e to the x. Perfect. All right. And the second derivative, let's just go ahead and get that out of the way as well. I'm writing f there. It's actually k. Let's be more precise there, Sherman. So k. Okay. Well, this one again, it's first times derivative of second, but we know that the 2 is going to be a 0. So we're going to end up with what, 4 e to 2x, and then of course the derivative of e to the x is just e to the x. So we are pretty easy right now. And one moment. Okay, sorry about that. Had to check on my microwave. So in order to find the relative extreme, we need to get the critical point. So in order to get the critical points, I need to take the first derivative and equate it to 0. Okay, so my first derivative here, I need to equate it to 0. So we're going to say 2e to the 2x minus e to the x is equal to 0. And this looks pretty easy, right? So it looks like we can factor out an e to the x. Okay, so I could have written that so much better. All right, so these are just little computational errors that I feel like maybe students can do as well. So anyways, I can factor an e to the x out. So by factoring e to the x out, I get e to the x. And what remains is 2 e to the x and then minus 1 is equal to 0. Okay, so I can figure out, all right, I can equate these to 0. So since e to the x is going to be greater than 0 always, the only thing that we really need to factor here, or I'm sorry, the only thing that we need to get is just simply the e to the x. So by setting e to the x equal to 1/2, because I'm dividing by 1 dividing by 2, so I'm sorry, so adding 1 dividing by 2. So I'm just working on this right here now. I got e to the x is equal to, again, I'm adding 1 and dividing by 2, so it's equal to the 1/2. And then in order to get rid of the e, I take the natural log of both sides. So I end up with x is equal to the natural log of 1/2. Okay. And again, I'm not messing with this because I can't ever get that to 0. So x is equal to the natural log of 1/2, and so that is going to be one of my critical points, the natural log of 1/2. And what I need to do now is I need to figure out, since I got the critical point, and maybe I shouldn't have circled that, put this in green. Yeah, I probably shouldn't have done that. Oh well. So now that I got the critical point, I'm going to plug it into my second derivative. Okay, so by plugging it into my second derivative, and let's put this down here. So k double prime of the natural log of 1/2 is equal to, and I'm not gonna write natural log 1/2 into this. I'm just gonna go ahead and put this into my calculator and get a solution real fast. 4 times e to the 2 raised to the 2 times natural log 1/2. I could just do natural log of 0.5. That's a lot simpler. Okay, so I get 0.5. Okay, and since 0.5 is greater than 0, then we have a relative minimum. Okay, so we have a relative minimum here at at the natural log of 1/2. So we know that it's going to be the bottom of the graph. So let's go ahead and show that here. I think I can fit this on the current page. Yeah, I can fit this down here in the bottom right. No big deal. Okay. So again, to me, that's a lot easier than doing the doing the critical points, figuring out the intervals, and then plugging in a test point. Are you positive or negative? And then going from there. So, as usual in math, there's always a faster way to do it in the next section, right? All right. So next, we're going to talk about points of inflection. So points of inflection are where the graph changes concavity, and we'll just put all this on one page and discuss. All right. So this is pretty important. So a point at which concavity changes from down to up or from up to down is called the point of inflection or an inflection point. Of course, you've heard inflection point before used, but probably not in a math course. In the figures below, point P is an inflection point. And then notice how we're going from concave down. Okay, well, you know, if you didn't have that point right there, you would say, okay, so, or you would ask rather, where do we go from concave down and then go to concave up, right? Because it obviously looks like it blends, right? But you know, point P is there to help you out. But that's what the inflection point is. The inflection point is exactly where we change from concave down to concave up. Right, and of course this is a pretty easy graph to look at, but what about this one, right? We can tell this is concave down, but again, where exactly do we go from concave down to concave up? And we see obviously it's at that point P, which we call the inflection point. Same with the last example. So how do we find the inflection point? Well, let's first of all, before we, I mean, obviously you can read this, but let's think about what we've done so far. So when we get to graphing equations, all right, obviously the original function is the graph, right? But what if we don't know how to, we don't have a graphing calculator, we don't have anything to graph it with, and so we don't know what it looks like. Well, we take the first derivative, okay? And then when we took the first derivative, we took that first derivative and set it equal to 0. And by setting it equal to 0, we found out some critical points, right? And what are critical points? Well, those critical points are where my graph has a relative maximum or relative minimum. Because when I set that first derivative equal to 0, that is where the slope of the tangent line is 0, right? It's a flat, it's a horizontal line. So that's a critical point. It goes from, you know, going up to down or from down to up. It's a relative minimum or relative maximum. All right, and then what happens if we set the second derivative equal to 0? Well, if we set the second derivative equal to 0, that is how we get the inflection point. The inflection point, if our function has an inflection point, it must occur at a value of x naught in the domain of f, where some x naught, and again, x naught is just a placeholder, right? I mean, they could have said a or b, it doesn't matter. It's where the derivative, the second derivative at that point, is equal to 0. Or my second derivative does not exist at that point. That is where the point of inflection occurs. So again, that's a little wordy, so let's get into a good old example here. All right, there's no C. Alrighty, so example 3A. So find the points of inflection on the graph. So we need to figure out where the points of inflection are. So far, again, we found the critical points where the derivative is 0 and where we go from increasing to decreasing or decreasing to increasing. Now we're going to find the inflection point exactly where it changes. Okay, so in order to do that, let's first, well, we have to get the second derivative, and if I recall, it was like 6. Well, heck, we'll just go back here. What was it? 6x plus 6. Yeah. So the I wonder if we actually need the second derivative. Whatever. Okay, so f double prime. There we go. F double prime of x, 6x minus 6. I forgot if that's what it was. I'm scared to go back pages because I don't want this to freeze. Yeah, 6x plus 6. Okay. There we go. All right, so the second derivative of our function is 6x plus 6. We did this in example 1, so no big deal. And what we need to do now is we need to take this derivative and equate it to 0. So by equating it to 0, we're going to figure out what the inflection point is. And of course, this is super duper easy, isn't it, right? 6x plus 6. If I were to equate that to 0, we'll just put it underneath it. It would just be x is equal to a negative 1, right? So x is equal to negative 1, and that's my inflection point. Well, what is the y coordinate of that? Well, we're going to plug negative 1 into my original equation, right? We just take the function at that point, and we can figure out, well, that's where my inflection point is. So if I were to do this, and again, I'm going to do some calculator work. We'll put this down here as f of negative 1. Keep in mind this is just f of negative 1, not f prime, not f double prime, and so that corresponds with my original equation. And f of negative 1 is negative 2. Let's fix that. Is equal to negative 2. Okay, so what does that tell us? Well, again, that tells us that's exactly where my inflection point occurs. And let's show a graph here. And again, this was the first example where my graph looked a little jank because I was even with my x coordinates. But of course, we can tell, you know, we up here, we derived these, all right, so nothing new. We had our critical point here, our critical point here, but our inflection point is right there smack dab in the middle. Okay, so that is the difference between concave up and concave down. And I don't know if this will help, and it's probably an easy concept for you to understand, but just in case it's not, I think the textbook should have done something like this, where it colored them differently, like that. All right, so we can see that we're concave down from negative infinity to negative 1, and concave up from negative 1 to positive infinity. And then B, we're just going to have to deal with that slash mark. Man, I forgot what the second derivative of that was too. I think it was a 4x, no, 4, shoot. What do we have? 4e I knew that. Okay, so f double prime, that's k again. K double prime of x was equal to a 4, sorry about that, 4e to the 2x minus e to the x. Okay. All right. So again, what I have to do is I have to figure out. I have to set this equal to 0, and by setting that equal to 0, I will have my second derivative. Not my second derivative, my inflection point. So we're going to do, can't necessarily do this as easily in our head, but we know we can factor out an e to the x. So e to the x leaves me with 4e to the x minus 1. Set that equal to 0. And same thing as before, my e to the x is always going to be greater than 0, so we're just going to focus on what's inside here. So we're going to add 1 and then divide by 4. So we're going to have e to the x is equal to 1/4. And so naturally, we take the natural log of both sides, and we're going to have, I'm so scared to move these. I feel like that's where my problem came. We're going to have x is equal to the natural log, and we're going to put a decimal instead of a fraction, 0.25. Okay, so at the natural log of 0.25, and that's pretty darn easy. What is natural log of 0.25? Negative 1.38. So at negative 1.38 being my x coordinate, that is where I'll have the inflection point for my second function that we did. Like so. So that's inflection points. And the rest of the examples, what we're going to do is we're going to just go straight from the bottom all the way to the top with absolutely no information. We're going to figure out how to graph a function without using a calculator. Oh man, sorry about that. So again, in our previous courses, we have learned how to sketch graphs, but pretty simple graphs, right? Again, all we did was we got the x and y intercepts, and then from there we graphed functions. And let me just kind of point it out here. There was one function we did. Maybe it wasn't. Maybe this is the next example. Yeah, okay, it's actually this example. Okay. So sometimes in pre-calculus or something, we didn't really know. I mean, of course, we knew what multiplicity was, and do we touch the x-axis? Do we cross the x-axis? All that good stuff. But sometimes, even with that information, it was really hard to figure out how to draw it. Well, we now have every tool that we need to figure out how to draw a graph because of these past two sections. Now, this says a strategy for sketching graphs, A through F, and let's see. Honestly, if I were to take out one of these, some of these, I don't know. Let's just do it. I mean, maybe it helps. I don't know. I feel like as a student, having just more things to memorize isn't good for the brain. Whereas if you just do something, it's just a lot easier. So first of all, we know that in order to figure out how to graph this function, we're going to need to take the first and second derivatives. Right, by taking the first and second derivatives, I'll get my relative extremas, and by doing that, I can figure out if I have a relative minimum or relative maximum using the second derivative. So, and honestly, I feel like between just those two, you're good to go. I hesitate to say this, and this is why I was looking at the steps. I hesitate to say this, but I'm not entirely sure, at least for these exercises, that concavity is too much of an issue because we can draw the graph without the idea of a concavity because we do know that we are uh, well, we have our relative extrema, right? But one thing that we didn't necessarily cover in this section that I think is pretty important is end behavior. Now, if you took a pre-calculus course, you are familiar with end behavior. And what I mean by end behavior, we're talking about what happens at the extremes of a graph. And so I'll give you a quick crash course on this because I think it'll really help. All right, so if our function here has an even um, an even exponent. All right, let's do just a quick sketch here. If it has an even exponent, it doesn't matter what's in here. The end behavior is that in the end, both sides are going to shoot up. Okay, if we have an even exponent. Now, if it is a negative x to the fourth, then they're both going to shoot down. So my point is, if we have an even exponent, they're going to be going the same direction. And so we see that here, right? And if they're odd, right, so let's just say if this is x cubed minus 2x squared. Right, if they're odd, then the end behavior is going to be down and up. And of course, if it is a negative, then it's going to be the other way. It's going to be up to down. Okay, pretty easy concept. I don't think I need to talk about too much more, but for examples like this, it's going to come in handy because, well, that's just more pieces of the puzzle that make it a lot easier to actually graph. So with that said, let's begin. Luckily, and I'm very thankful for this, this is a pretty easy function to find the derivative of. Okay, so f prime of x is just going to be, looks like 4x cubed minus 4x. And then f double prime, right, the second derivative, is just going to be 12x squared minus 4. Okay. So I got the first and second derivatives, and now I need to find the critical values. So my critical values, again, are when I set my first derivative equal to 0. So start here with the critical value. So we'll put this as critical, we call them critical points. Let's just call them critical points. So critical points are when I set my first derivative equal to 0, and then I solve. So let's go ahead and solve. It looks like I can factor out an x. It looks like I can factor out 4x. So 4x, I have 4x squared minus 1 is equal to 0. I don't know why I put a 4 in there. That's better. Alrighty. Well, obviously, one of these solutions is going to be x is equal to 0. Right? That's this one. I set 4x equal to 0. X is equal to 0. The next one is going to be the square root of 1, which will be positive and negative 1. Right. So my critical points are 0, positive 1, and negative 1. Right. And so real quickly, let's go ahead and figure out what those points are, exactly what those points are, right, the actual y coordinates. So my critical points are going to be, right, so if I plug in a 0 here, well, f of 0 is just going to be 0. So one of the critical points is 0, 0. If I plug in a positive 1, well, that's going to be 1 minus 2, so it's going to be negative 1. So, and if I plug in a negative 1, it's going to be a negative 1 as well. Yeah. Okay. So again, my critical points, and we'll put this down here, that is f of, well, no, I think that's confusing. Again, these are just the coordinates when I plug my x values into my function. Okay. So these are the coordinates of my critical points. The next thing we need to do is figure out if they are minimums or maximums. So again, 0, -1, +1, that's not hard to figure out, or not hard to remember. So we're going to do, okay, so again, critical points were 0 and ±1. My second derivative was 12x squared minus 4. 12x squared minus 4. Okay. So again, I'm going to plug these into my second derivative, and I'm going to figure out if I have a relative maximum or a relative minimum. All right, and we can kind of maybe do this in our head, but let's just go ahead and do this. So f double prime of 0. Okay, well, that's just going to be -4. Double prime of -1. -1. It's going to be, first of all, let's fix this. We're looking at a +8. Yeah, and then f double prime of +1. It's going to be the same thing. It's going to be 8. Okay, so looking at this, we see that -4 is going to be less than 0, so that's going to be relative maximum. So this is going to be a maximum. And then the +8s, well, those are greater than 0, so they're going to be a minimum. So, and I'm pretty sure we can give a rough graph here, right? I think for graph sketching, I don't think I should probably cheat for this, huh? So my points are what? Oh, no, forgot. Oh, 0, 0, 1, -1, -1, -1. Okay, so looks like I don't have to go too far out here. Alrighty. So my points were at 0, 0. Oh, it's on the line. 0, 0. We're at -1 and -1, so right here, and at +1, -1. Yeah, that should be a negative. Okay, so these are our 3 critical points, and looking at this, we're told if they're relative maximums or relative minimums, right? Well, f of 0, we said was a maximum, so what we're going to do is we're just kind of point these downward. And let's actually make a different color. We're going to point this down because it's a relative maximum. Well, these 2 points, -1 and +1, we said were relative minimums, so we can, put a little cup right here, like that. And realistically, that's it. We don't have to do too much more than that. Like I said, the last thing would kind of tie into our pre-calculus thing, but in behavior, because we know in the end, since it's an x to the fourth, we know that we're shooting up like this. So all we have to do here is just connect the dots, and we have our function. Right? I think it. All right. You don't necessarily need inflection points to actually graph the equation. Okay, but since the problem is asking for us to actually find the inflection point, we're going to go ahead and find the inflection points. Okay, so we're going to set this second derivative equal to 0 to find the inflection points. So let's go ahead and put this over here to the right. Let's divide this a little bit. Let's put this on this page because I don't think, yeah, we'll just keep it on this page. So if I set this equal to 0, so 12x squared minus 4, set it equal to 0. Looks like we can, again, factor out, looks like just a 4 this time. So 4, and we got 3x squared minus 1 is equal to 0. We don't care about the 4, so we can just simply say 3x squared minus 1 is equal to 0. And then we can do the rest of this in our head, right? We add 1 to both sides and divide by 3, take square root of both sides. So we end up with the square root of 1/3, right? So we'll plus or minus square root 1/3. Okay. So these are my inflection points, and I need to get the y value of the of this. Oh, this is gonna be ridiculous. Okay, so I need to figure out what the y values are. So I got to plug in this value into my original function to figure out what the y coordinates are. So let's do that. So put I, P for inflection point. One of them will be, we'll do the positive square root of 1/3, and also we can actually fix that to 1 over the square root of 3, right? 1 over the square root of 3, and then one's going to be the negative of it. Alright. Alright, forgive me, gotta do some behind the scenes calculator work. Luckily, when I change that, I just have to put a negative in front. Okay, so I end up with a negative 5.88 for a positive, so negative 5.88. 5.89. And then for the negative, it's also a negative. Cool. Okay. So negative 5.89. Okay, so again, when it comes to actually graphing these, the inflection points, in my humble opinion, aren't necessarily that important. But like I said, the problem wants us to find them, and so does the homework and the test too, sorry. So we found them. And let's go ahead and give you the nice pretty graph, which also includes our inflection points. This problem spans some pages, didn't it? And we'll put this down here. All right. So same thing. I guess I was a little more wild on my end behavior, but not a big deal. Oh, it is a big deal. It is a big deal because I should have probably got my X-Intercepts. Yeah, it turns out to be a big deal. So let's go ahead and do that real quickly. All right, and then this is just a this takes us back to algebra 1 or something like that. We just have to find the x-intercepts. All right, well, how do I find the x-intercepts? I have to set y equal to 0. And so basically all I have to do with that is take our original equation, which was x to the 4th power minus 2x squared. So let's do that. And we set it equal to 0, right? That's how you find the x-intercepts. So by doing that, let's go ahead and factor out an x squared. We end up with x squared minus 2 is equal to 0. And of course, we have one of the x-intercepts is going to be 0, which is this x-intercept right here. And the other one is going to be the square root of 2, which is going to be about a little bit about right here. Let's put this in red. About right here. This is awful. Now we can shoot through. Now we can shoot through. close enough. But anyways, that's how we sketch a graph. We have all the information we need, and of course, obviously, you can, with technology, you can graph this on your own. But if you didn't have it, there you go. The last example, it's not as nice and neat. We don't have to necessarily worry about any behaviors or anything, but we do have to worry about the domains here. Right. So looking at this particular equation, let's go ahead and take the first and second derivative. All right, well, the first derivative should be pretty easy. If you recall, it's going to be just simply the derivative of the argument, right? The argument over the argument, right? So it's just going to be 2x over x squared plus 6. And then the second derivative is going to be a little more complicated. So what I'm going to do is I'm going to do the computation down here and then put it nice and neatly up here. Okay, so it's low d high, so x squared plus 6 times the derivative of the high, which is 2, minus high d low, so it's going to be 2x, and then the derivative of the bottom is also 2x. Right. All over low squared, which is x squared plus 6 squared. Right. And if we clean this up, we end up with 2x squared plus 12, so 2x squared plus 12. And then it looks like plus 4x. No, I'm sorry, minus 4x squared. So minus 4x squared. And then all over the bottom. All right, so we're going to go ahead and combine. This is my numerator. All right, my denominator is, I don't really want to touch that. So my numerator, I can combine the x squared. So I'm going to end up with a negative 2x squared and then plus 12. And then I'm going to put that over my denominator, which is x squared plus 6 quantity squared. There we go. Okay, so I got my excuse me. I got my first and second derivatives, and so I need to figure out my critical values. Okay, so again, my critical values, what I'm going to have to do is I'm going to take my first derivative, and I'm going to set it equal to 0. Right. So in order to do that, we take the first derivative. All right, well, it's actually pretty, I wouldn't say pretty easy, but looking at, we don't have to do any computation here actually. I mean, we could, but it's pretty easy. But by looking at the first derivative, when does this equal to 0? Okay, well, the denominator will never ever be 0, right? There's no value that I can put in for x that'll make it equal to 0, because if you square anything, it's either going to be 0 or a positive number. So the denominator will never be 0. However, the numerator will be 0 when x is equal to 0, right? Because 2 times 0 is 0, and then 0 divided by anything is 0. So that's pretty easy. So what I'm going to do is I'm going to plug that second, well, no, sorry, so let's put this as critical point blue. So my critical point is when x is equal to 0, right? So now we got to figure out what the coordinate of that would be. And of course, by figuring out the coordinate, I have to figure out what the y value is. And figuring out the y value, well, all I'll have to do is just plug this 0 into my original function. So I'd have the natural log of 6. So my point is going to be 0 and the natural log of 6. So this is where my critical point is located. So I need to figure out, is my critical point a relative maximum or relative minimum? Right? Well, what I have to do here, again, I have to figure out, what did I put for this? I put, okay. Plug in 0 into my second derivative, and by doing that, we're going to do h double prime of 0. And yes, the arithmetic is pretty darn easy. should actually be a 12. Okay, so 0 squared, so it just becomes 12 over 36, which is 1/3. So h of 0 is going to be equal to 1/3, which is greater than 0. So this tells me that this is going to be a relative minimum. Okay. So without even doing the inflection point just yet, let's go ahead and figure out what this graph might look like. And again, I don't necessarily think the inflection point is necessary. It's just we need to know it for later sections. So if I were to graph this function, again, we had the critical point at 0, so that was at this point right here. Okay, and we know that that was the relative minimum. Okay. Well, I'm sorry, 0 and natural log of 6. What is the natural log of 6? Natural log of 6 is 1.79, so about 1.8. So let's make some tick marks before we begin this. Let's make them big, actually. So 1, 2, 3, 4. Okay, so the natural log of 6. So this is my critical point, and 0, the natural log of 6, is about 1.8. So we're going to go up here to 0 and 1.8. So about right here, maybe. Okay, all right. So I know that's a minimum. So I know that's going to be shooting up this way somehow. Okay. Well, that's really it. That there's nothing else that we need to do about this. We could figure out. Okay, so to graph this, we also need to find the x-intercepts. All right. Well, where does this function, the original function, if I set y equal to 0, where would x or what would my x solution be? Well, it would be unsolvable, right? It's an imaginary number. We can't do that. So that tells me that there is no x-intercepts. And of course, we've seen problems like that before in other classes, where if you don't have an x-intercept, whenever you solve for x, if you get something that's undefined or an imaginary number, we know there's no x-intercepts. So I know that my graph looks something like this, right? But again, we are asked to find the inflection points. So let's go ahead and find the inflection points. So we have to, oh gosh, it looks horrible actually. So in order to find the inflection point, we have to set the second derivative equal to 0. That's actually not too bad, because, let's put this on the next page. We're getting a little cramped here. X, 2x squared plus 12, just rewriting real fast. Okay. All right, so again, in order to find the inflection point, we have to set this second derivative equal to 0. Well, again, lucky for us, I mean, obviously if we set it equal to 0, we can kind of forget about this because we multiply both sides by that. So we really only focused on this numerator here. So that makes it pretty darn easy. And real fast, what I mean by that is this. That was plus 12. What am I losing my mind here? We multiply both sides by the denominator, and we still end up with setting this equal to 0. So that's why I was saying that we can kind of forget about that. So we multiply both sides by the denominator, and we just simply end up with this equation here. And this one's pretty darn easy to solve, right? We're going to factor out a 2. We end up with an x squared plus 6 is equal to 0. And that's a minus. Oh man, I'm having a. Well, no, I'm not. Okay, good. it's in negative. That's what I did. Sorry about that. All right, so I factor out a negative. And so we end up with an x is equal to the square root of the plus or minus square root of 6. Okay. So this tells me my inflection point's at plus or minus the square root of 6. And then if I take the y coordinate of that, I need to plug in the square root of the plus and minus square root of 6 into my original equation, which was natural log of x squared plus 6. So let's write that over here real fast. All right, so I'm going to plug in my x value to get my y value out for my inflection point. So that's going to be all right, it's going to be the exact same for both, 2.485. So if this is my x value then of my inflection point, my y value is going to be the exact same for both. So I'm just going to kind of put the notation here. I know it looks weird. It'll look weird on the notes, obviously, but if you are paying attention to the lecture and corresponding them with the notes, they will make sense. So did I have a second page? All right. Let's go and get a nice clean looking graph now. And my graph wasn't too far off, obviously. It's pretty easy to draw. All right, so we obviously had our relative minimum here, which we did, and then we just got our inflection points just now. And I'm pretty sure that's all we wanted to do was graph the function and get the inflection points. And that mercifully ends today's lecture. All right, so those of you that stuck around to the end, good job.